All right, so we've been talking about rotational motion the last week or so, this new quantity, the moment of inertia. We've been trying to make connections between rotational quantities and translational quantities. And in this video, we're going to introduce a new quantity, torque, which is our rotational analog to force. And so I just want to go through this example here that I've got sketched and explain why we need a quantity such as torque to begin to explain the behavior of extended objects that are able to rotate. So what I have in this figure here, I've got this blue rod, and you can think that we're just maybe looking straight down on the rod. Maybe it's resting on a table, and then I've got this this axle here right through the middle. And so the rod is sitting on a table, but it's pinned down at the middle, so it's free to sort of rotate around that center point. And what I'm going to do is I'm going to apply a force F downward on this side and upward on this side. Same amount of force, but in opposite directions. And so when I do that, what's going to happen to the rod? Well, when I do that, the net force on the rod, I'm adding a force down and a force up. This rod is at rest, and I add these two forces, apply these two forces to the rod. Well, the net force is going to be zero because the two forces that I'm applying are in opposite directions but the same magnitude. So if we think back to our force analysis, net force is zero. That means the translational acceleration is going to be zero. But if we think about what actually happens when you apply a force on these opposite edges in the way that I'm doing, this object's going to start to rotate. It's at rest. After I apply these two forces at the locations I've designated, the thing starts to rotate. And so that means there must be an angular acceleration because the object was at rest. So omega was zero. There was no rotational, no angular speed. There was no rotation. And then after I've applied these two forces, all of a sudden we are rotating. And so we need a new quantity that allows us to characterize or analyze what's happening with extended objects that are able to rotate. And this new quantity we call torque. And so torque, the symbol that we use is tau, and torque is a vector. And it's a vector quantity that's connected to R and F. So to have a torque generated by a force, you need to know the magnitude of that force. You need to know how far away that force is from a rotation point. So in this case, my rotation point is here, so my distances are r, whatever that is. And then you'll notice that the vector r and the vector f are multiplied together with the cross product. And so that means the result of this product is a vector, so tau torque is a vector. And the cross product is defined as, the magnitude of the cross product is defined as just take both vectors, the magnitudes, multiply them together, and then multiply by the sine of theta, theta being the angle between the two vectors. And so if you look at my picture over here, I've got a rotation point down here, I've got this blue rod, and then I'm applying a force out here. And so if you look at the vector r, so that's the vector that points from my rotation point all the way out to where the force is applied. So here's r, here's f, and so the angle between those two vectors is theta. And so if you want to get the magnitude of the torque that's generated by this force being applied at this location, the torque about this rotation point, then you've got to take into account this angle theta. So the magnitude is r, f, sine theta. And so I want to stress here that to calculate a torque, right, to designate what r value to use, you must pick a rotation or a pivot point. So if you pick this spot right here as your rotation point, well, then your r is a different value than if you pick your rotation point over here. Right, so absolutely must designate a rotation point or a pivot point when you're calculating the torque. So this expression right here can be interpreted two different ways. The first way that the expression can be interpreted, so r f sine theta, you could group these two together, and you could interpret this torque value as r multiplied by f sine theta. That's the component of the force that's perpendicular to the r vector. And so I've drawn this here, my r vector out to where the force is applied, and then I've broken my force vector up into the component that's perpendicular and the component that's parallel to this vector r. And so when you're going to calculate torque, you can think of the calculation as how much of the force that's being applied, how much of it is perpendicular to this, this is called the radial line. So how much of the force is lying perpendicular to that radial line. The other way that you can think about this expression is instead of f sine theta, you can think of r sine theta. So you can think of the perpendicular distance to the force that's being applied. So what does that look like? Well, here's my force that's being applied, and then all I do is I extend this line, and then I project the radial line so it's perpendicular, so it hits perpendicular to this. This is called the line of action. And so they make an angle of 90 degrees. So this is called the moment arm. This is the perpendicular component to the line of action. So you take, in this particular interpretation, you take all of the force and you multiply it by the amount of the distance that's perpendicular to that line of action. And you'll notice that this angle here is theta. So this, the length of this side here, remember this is r, so the length of this side will just be r sine theta. So those are the two ways that you can think about calculating the torque. You can either determine how much of the force is perpendicular to r, or you can figure out how much of r is perpendicular to f. Right? Those are the two approaches. And the last thing I want to mention about torque, since torque is a vector, if you want to find the net torque, then you just add up all of the individual torque calculations in your problem. So in this particular example, I've got one force being applied, so I would only be calculating one torque term, but you could imagine if I've got a force here, maybe I've got a force here, maybe I've got a force here, then I would have to do multiple torque calculations, and then I would add up the individual terms to get the net torque. Now, the convention here is exactly like the convention for omega, where if the torque that we calculate, so in this case, let's look at this one. So the torque, so we've got our force this way, we've got r along that axis. So if we apply this force in this direction, then that is going to cause an angular acceleration this way. And so the object will begin to rotate in the clockwise manner. And so this convention, same as omega or alpha, we would call this a negative torque. And if the torque that's being applied generates rotation counterclockwise about your rotation point, then we would call that a positive torque. Right? So that's just the convention. Torques that would give rise to clockwise rotation we'll call negative. Torques that would give rise to counterclockwise rotation we'll call positive. Right? And so that's how, when you add these all up, you could get net torque equal to 0, because some of the torques could be positive and some of the torques could be negative. All right, so now that we have torque defined, then we can start to think about what this means for an object that can rotate, and what it means for how to change the rotational motion of an object. And again, the rotational stuff we're talking about has direct analogs to translational quantities and phenomena that we've been studying previously. And so if we think about Newton's second law, let's forget the rotation for now. Newton's second law, that tells us the net force that's acting on an object, that gives rise to an acceleration. And so that's Newton's second law. Well, for rotation, if there's a net torque acting on an object, then that is equal to I. Remember, the moment of inertia is the rotational equivalent of mass, so I times alpha. And so you can see the analog here. Torque is the rotational equivalent of force. I, moment of inertia, rotational equivalent of mass. Alpha, rotational equivalent of acceleration. And so what this means is if we have a problem where we're trying to determine whether or not an object stays at rest or stays rotating at constant angular velocity, we would analyze the problem and determine the net torque. And if the net torque is non-zero, then that will result in an angular acceleration. Much in the same way that we would have force problems where we would ask, what's the net force on the object? If the net force is non-zero, then the object would accelerate. Exact same idea. Now, another thing that we can make connections to is the work-energy theorem. Remember that the work-kinetic energy theorem, if there was work done by a force, then that would correspond to a change in kinetic energy. So the work done as the object goes from A to B corresponds to the change in the kinetic energy from A to B. And remember that for kinetic energy for an object that's rotating, that would mean 1/2 I omega squared at A and at B. So whether or not the object speeds up or spins up or spins down, if the angular speed is changing, that would correspond to a change in the kinetic energy. And so I would want to remind you our definition for work back in chapter 7, I think, was that you would look at the dot product of F dot dl. So you would apply a force over some displacement from A to B, and that would correspond to the work done by a given force. We do nearly the exact same thing for rotational equivalent, but now our rotational equivalent of force is torque, and our rotational equivalent of changing position would be changing angular position. And so we evaluate the integral of the torque that's generated that we're examining, the torque that's generated, and we integrate over the entire change in angle during which this torque is applied. So we integrate from angle A to angle B. So exact same approach, just with our angular or rotational quantities. And then the last thing that we can think of here is we talked about the power generated by a force acting on an object that is moving with a certain velocity. And that power is the dot product of the force, so dotted into the velocity vector. Well, for rotation, same idea, but instead of force, it's the torque that we're considering multiplied by the angular velocity of the rotating object, and that corresponds to the power at that particular moment. So there is a table in the book, table 10.7, which is on page 523. And so this table has all of our rotational quantities that we've been talking about with the translational quantities next to them, so that you can start to make those connections between moment of inertia and mass, kinetic energy for rotation versus translational, Newton's second law for rotation versus Newton's second law for forces, and then these work, energy, power relationships. So this is the framework that we're going to use to start to solve rotational problems, so rotational dynamic problems. And I'll be putting together a Lightboard video to walk through an example or two before our next class. So I'll be adding that to Sakai probably on Monday, so look for that.